Welcome back everyone to Learning by Teaching. Today we're in statics and we're going to do 719, okay? So it says determine the internal normal force, shear force, and moment about point C, okay? So we have our point C, we want to know what's the internal forces in here, okay? So the first thing that we need to do in order to solve this problem, and basically every single problem in statics, free body diagram. Okay guys, so we're going to draw a free body diagram of this beam, is we can call it like this. Now over here A, we have a pin connection, so we're going to have our AY, AX, okay? Then this rope will cause a tension going into this direction that we don't know what it is, so let's just call it T, okay, for tension. Now we also have this distributed load in here, so let's replace it by a normal force, just by one force in here, and then we need to do the area of this square, so we need to know this area. So in order to do the area, we're going to do the area of a rectangle. So what we're gonna have? Well, we're gonna have the height, which is 150, multiplied by its base, which is 8 plus 4, that will give me a total of 12. And then if we plug this into the calculator, this will give us 1800 pounds, okay? So now we know that this is equal to 1800 pounds. The last thing that we're missing is where are these guys located? What is this distance from here to here and here? So since this is a square, the location of this force should be in the middle of the square. So if the total base is 12, so it should be 6 feet apart from 6. So this should be 6 feet, and then, well, this should be 6 feet too. Obviously doesn't seem really out to scale, but it is okay for our free body diagram so far. Okay, now the last distance that we're missing is this tension T with respect to our horizontal beam. And if we check it out in here, we got 2 feet and then we got 0.5, so this will be an equal of 2.5 feet on this direction. Okay, now we can apply the summatory of forces in the x direction, assuming that going to the right is positive. And what do we have? Well, we have ax minus t should be equal to 0. So from here we can conclude that basically the ax it's equal to my tension T, okay? The next thing that we can do is summatory of forces in the y direction, assuming that going up is positive, well, we'll have ay going positive. We got negative 1800 pounds, and that's all. So this should be equal to 0, and from here we can conclude that ay is equal to 800 pounds. Okay, the last thing that we're going to do is that we're going to apply the summatory of moments. Counterclockwise is positive, and I'm going to choose my point A, that way I can cancel ax, cancel ay, and the only unknown I have is t. So okay, so what do we have? Well, we'll have, first I'm holding here, and then these 1800 pounds will want to rotate me clockwise, so I got negative 1800 pounds multiplied by the distance, which we figured out it was 6. Then what else do we have? Well, we have the unknown t, so I'm holding here, and then my force wants to go like that, so this member will want to rotate counterclockwise, so we'll have positive t multiplied by the distance, which is 2.5, and this should be equal to 0. If from here we solve from t, we will have 1800 pounds multiplied by 6, all divided by 2.5. Okay, so we'll figure out that t will be equal to 4,320 pounds. I'm sorry, So we can plug it in back into our AX. Now, the main goal of doing all this is that we want to know the internal forces at my point C. So why am I doing this? Well, I'm doing this because I want to do the method of section, like I'm gonna cut my beam at my point C. I'm gonna name it section 8A. And I wanna work with my left side. I don't wanna work with my right side because my right side looks really complicated. So let's just do a free body diagram of my section AA. Okay, so what do we have? Well, we'll have in here, we'll have my point A. This in here will be my point C. And if we check our first free body diagram, we'll have AX, AY. So we'll have AY, AX. We can also check from our main problem statement that this is 3 feet apart. And then we need to also figure out how much is this force of this new rectangle that we have, okay? So since we know that from here to here is 3 feet, we need to find our new force rectangle that I'm going to call it rectangle 2. The height, it's the same, which is 150, but the base change, which is just 3. If we multiply this, we'll get 450 pounds. And its location, its new location is going to be at the middle of those 3 feet. Okay, so we'll have 450 pounds in here. And then that middle obviously should be 1.5 feet. Okay, so after we're done with this, knowing that we cut at C, so let's erase that C, we will have an NC going away, a BZ going down because we're on our right side, and a moment, internal moment C. Okay, and we apply our summatory of forces. So let's start with the summatory of forces in the X, assuming that going right is positive. Then we'll have what? We'll have AX, positive NC. So AX plus NC. And I have nothing else, so it should be equal to 0. From here, we can conclude that NC is equal to negative AX. So since we know AX, will be negative 4,320 pounds. Okay. Next, we can do the summatory of forces in the y direction. Going up is positive. And what do we have? Well, we'll have positive AY, negative 450 pounds, and negative BZ. Okay? Since we want to solve for BZ, what do we have? We'll have AY, which is 1800 that we found in here. Then we'll have negative 450, and this will give us 1350 pounds. Okay, and the last one that we need to find is this MC, and in order to do that, we're going to do the summatory of moments around my point C, so we don't have to worry about BZ neither NC. Okay, so assuming that going counterclockwise is positive, and we apply the summatory of moments around my point C, what do we have? Well, AX doesn't contribute to anything. If I'm holding here and this force AY, this will want to rotate me counterclockwise. So we'll have clockwise, we'll have AY multiplied by the distance, which is 3 feet. Now this 450 holding from here will want to rotate me counterclockwise, so we'll have positive 450 times the distance, which is half of our length, meaning 1.5. And the last thing I have is the internal moment at point Z. And all this should be equal to 0. Okay, so if we solve for MC, we will have AY, let's put it into its numerical value, 1800 multiplied by 3. Since this is going to the other side, this becomes positive, so minus 450 times 1.5, and let's see how much this is. So if we plug this into our calculator, we will find out that this is equal to 4,725 pounds per feet. Okay, so we got our internal normal force, internal shear force, and our internal moment. Okay, if you guys like the video, please push the like button, subscribe, and I'll see you guys in the next one.